Hello again. It's 9 o'clock at night. Nope, it's 10 o'clock at night. I just got home from my other job and I'm so happy to finally make this video for you. All right, tonight we're going to talk about vector equations and parametric equations, and this is the final chapter on. And I'm sorry, I have a sore throat because I've been talking all night. Vectors that we're going to do this year. And so I thought I'd start out with vector voyage because you're familiar with that problem. Most of you are, unless you didn't do your classwork. So we're going to graph direction, and we're going to make each square in my graph here equal to 100 miles. So 1 square is equal to 100 miles. And I know there's some like weird squares that you can't see. I'm sorry, I don't know why that happened. But I'm going to make this my origin. Well, at least the x-axis is here. So we'll make that the x-axis. And then we'll make this the y-axis. And this point here is 0, 0. Right there. And you'll notice that I have a cruise ship waiting to set sail. Oh, that's bad. Okay, let me see if I can just choose the cruise ship. Okay, I think I got it working now. So I have this cruise ship here ready to go. Oh, don't go bigger, please. And if we look at where he is, he's 200 miles east of the origin and 600 miles north of the origin. And so my starting point would be 200, 600. Okay. Every month I travel east 400 miles. All right, so every month I move 1, 2, 3, 4. So that'd be after month 1. So this would be my starting point times 0. This would be after 1 month. And 2 months later, 1, 2, 3, 4, I'd be here. 3 months later, I'd be here. Oh, and we probably should move the boat. Nope, we're not moving the boat. The boat stays. You'll notice I called this T3. That's because time starts with T. So that's my scale for time. If I wanted to describe any of my x values where I am, well, since I'm starting at 200, east of the origin, and I add 400 miles every month, that's my equation for where I am in regards to the x-axis. Okay, you know it's never that simple. This time I'm going to redraw my axis. There's my x-axis. There's my y-axis. That was my starting point. Every month, the current pushes me 100 miles south. So we still have the same scale. We still have the same starting point, 200, 600. After month 1, though, this is month 1, I'm further south because the current is pushing me 100 miles south. After month 2, I'm another 100 miles south. After month 3, and so on. And so if I wanted to describe where I was on the y-axis with regards to time, I could say that y is equal to my starting point in regards to the y-axis minus 100t, because I'm going in the negative direction, 100 miles every single month. Okay, now it's time to put this all together. So let me go back and draw my axis in again one more time. There's my x-axis and my y-axis. So with the current and the power of the ship, I'm traveling east 400 miles and south 100 miles. So I'm moving on a vector this way. That's after time 1. And month 2, 400 miles east, 100 miles south. So I'm not moving in a straight line anymore. And that was my initial time. At any moment, I could say that x is equal to 600 plus, I'm sorry, that was the y value. It's getting late. 200 plus 400t. And y is equal to 600 minus 100t at any time. And that describes my x position here. So I'm graphing position on this axis, and I'm also graphing position on this axis. So it's position versus position. Okay, and then after 3 months, I've moved over 4 more squares and down another one, and so on and so forth. So at any month, I could describe where I am with respect to the origin with this equation here. This is called a parametric equation. And the parameter in my parametric equation is this here, and that's time. And that defines position anytime after my initial time, t0. So if I wanted to know where I was going to be after 5 months, I could just put in a 5 for time. And figure out exactly where I'd be. And I would be 2,100 miles east of where I started, east of the origin, and 100 miles north. Oh, look, there are pirates traveling through. There's a pirate ship coming. Oh, maybe there's 2. Nope, just 1. And it's going to try to intercept our cruise ship in order to steal all its stuff. Let's see if we can figure out who the captain is. Oh, it looks like the famous bad boy Logan. Look what that vaping's done for him. And look, he has no other options for jobs other than being a pirate because he didn't go to college. All right, he's going to try to rob that ship. Maybe the ship will go faster than he is. Let's figure out how fast it goes. So if it moves 400 in the x direction and negative 100 in the y direction, what would its velocity be? Well, that's going to be the magnitude. 400 squared plus 100 squared. This is called my velocity vector. That's how fast I'm moving. And you'll see that he's moving about 412 miles a month. Fortunately, Captain Logan can't get out of bed in the morning and doesn't move much faster than that. Okay, let's do another example. This time I have a yacht club here, and up here at 212 is my yacht. That's my starting point. And this starts at 12 noon. All right, so every hour it travels in the direction of 4, negative 3. You guessed it, that's my velocity vector. So how fast is it traveling? Well, it is 4 squared plus 3 squared. So it's traveling 5, we'll go with kilometers per hour. Okay, so if I were to plot that, this would be t0, because I'm starting at 12, and I'd go over 4 and down 3. 1, 2, 3. So this would be t1. At t2, I'd be here. At t3, I'd be here. Now let's get the parametric equation. X is equal to my starting point, 2. It's kind of like the y-intercept, sort of. And every unit of time, I add 4. And my y, where I am with respect to the y-axis, is I'm starting at 12, and I subtract 3 every unit of time. And those are that's my parametric equation. Now if I want to turn that into a vector equation, it's really simple. It's if I make vector r equal to xy and vector a, let's make that darker so you know it's a vector, equals a1 b1, and vector b equals b1 b2. That's a2. It's getting late. Then my vector equation is xy equals a1 a2 plus t b1 b2. It's as simple as that. If I go back to my parametric equation, I can turn this equation into a Cartesian equation. If I solve x for t, I get x minus 2 divided by 4 equals t. And if I solve the y-coordinate, the y component equation for t, I get y minus 12 divided by negative 3 equals t. These both equal t here, so I can set them equal to each other. And I can solve that. So that I'd have to multiply both sides by -3. That's going to clear this side, and I'd multiply both sides by 4. That's going to clear this fraction, and I'd end up with -3x plus 6 equals 4y minus 48. And when I put this in standard form, let's see, I get 3x plus 4y equals 54. And that's the Cartesian equation for that vector. Okay, so first example, I want to find the vector equation and the parametric equations of a line passing through the point 1, 5 with a direction of 3, 2. So 1, 5 is going to be my initial point. Okay, so that's my initial point. And that's my x and my y coordinates. And then 3, 2 is my velocity vector. And time is my parameter. And that's my equation. That's my vector equation. Okay, so the parametric equation is just x equals 1 plus 3t and y equals 5 plus 2t. It's as simple as that. By the way, how fast am I going? Let's check. So I need to look at the velocity vector because that's the movement I make every month, or every unit of time. Sorry, that we don't know that that's a month. So that's 3 squared plus 2 squared, which equals radical 13. That's how fast I'm going. All right, my second example. Some particle moves such that x of t equals 2 minus 3t and y of t equals 2t plus 4t. And t is greater than or equal to 0. Find the initial position of the particle. So the initial position, -3 and 2 would be the velocity vector. So the initial position is going to be 2, 4. So that's the initial position. If I want to know where I am, that's t equals 0. At time 1, I have 2 minus 3, which would be -1, and y would be 6. At t2, I'd have -4, and 4 plus 4 would be 8. At t3, I'd have 2 minus 3 times 3 would be 9, so -7. And 6 plus 4 would be 10. And we could keep going. If I draw that on a graph, roughly t0, I'd be at 2, 4. I'd start here. At t1, I'd be at -1, 6. So I'd be about here. Could draw that. t0, t1, t2, t3, t4. I apologize for the sloppiness of this graph. All right, and then the speed is just going to be the velocity vector. So that'll be 3 squared plus 2 squared, which is 9 and 4, so radical 13 again. I think I must have done the last one wrong, because we didn't move at 3, 2. Oh well. All right, here's one for you to try. Stop the video, try this out, and then turn it back on and check your answers. Okay. Hopefully you can see that the starting point is 7.5 here, and that my velocity vector, because I move every unit of time, it's associated with the time, 6 units to the right and 8 units down. That's the velocity vector. So my speed is 6 squared plus 8 squared, which gives me the square root of 100. And the square root of 100 is 10, so 10 meters per second.